Hello and welcome to our 23rd session. Today we're going to start on the bipolar junction transistor, and we'll be looking at some general characteristics of the BJT, base current, emitter efficiency, and finally, if we get there, hopefully we'll be able to start on the current voltage characteristics, the IB characteristics. Let's start off with the finale to Beethoven's Egmont Overture, Opus 84. Exciting and incredibly powerful piece. You'll hear the different transitions from death to resurrection to struggle and finally to victory. And I'll see you back in about 3.5 minutes. Okay, so these are some of the topics we'll be covering in today's session. We'll be covering up some loose ends, specifically on the PIN diode, and then on a little bit of a kind of a trick, how to, maybe not a trick, but some ideas on how to tell whether something is in forward bias or reverse bias, because that's really important. We'll be going between forward bias and reverse bias, back and forth in the bipolar junction transistor. So then we'll be looking at, just for a minute, reviewing the device tree, looking where the BJT, or the bipolar junction transistor, fits into our overall structures that we're looking at in this course. And then we'll be looking at some qualitative aspects of the bipolar junction transistor, specifically the currents, operation, and we'll be looking at the efficient operation of the BJT, expressing the emitter, something called the emitter efficiency, and we'll say what's all that about, and finally we'll end up with another video clip. Okay, we'll start with some loose ends. Last time we were talking about the PIN diode, the P intrinsic N diode, and we said that there were three regions, the P, the I, and the N, and each of them had different dopings. The P was doped, obviously P, the intrinsic was very lightly doped, close to intrinsic, and the N, of course, was doped N-type. So here we see those three regions written out explicitly. This is from our previous session, and since the P was doped 10 to the 16th, and the N was doped 10 to the 15th, N to the 15th is 0.3 electron volts above intrinsic, and another order of magnitude is 60 millivolts higher, so 0.3 plus 0.36 is 0.66. That's the total drop across this three-layer structure, and we want to find out where the voltages are dropped, which gets more voltage and which gets less voltage. And I think we mentioned last time that most of the voltage we're going to claim was dropped across the intrinsic. This is the middle region, the I region. And we can show that by, first of all, solving for the widths. And we did that in the last time. But remember, it was a quadratic equation. We used the quadratic formula to solve for, I forget which one it was, Wn or Wp. But once we know Wn, we know Wp. And you'll notice here that Wn is about 1/10. It's actually not about, it is 1/10. The depletion region on the N side is 1/10 of the depletion region on the P side, because the P side is the lightly doped region. The N sub A is 10 to the 15th, and N sub D, the N doped, is 10 to the 16th. So the lightly doped region has a wider depletion width. The heavily doped region has a smaller depletion width. And we put those numbers into the formula, and we find that indeed this is the middle region right here. The middle region has about 0.5 volts of the 0.66, which is basically the whole thing. And then the lightly doped region has 10 times the voltage dropped across it, which is very small, and the heavily doped region has a very small amount of voltage dropped across it. Okay, so the next loose end that we'll be covering is how do we determine the sign for forward and reverse bias. So I'm going to give a little bit of a trick on how to do that. It's quite logical, and hopefully it'll make sense. Here, of course, we have the N-type, which is heavily doped, the P-type, which is lightly doped. The N depletion region has positive ions. These are the donor atoms that have given up an electron, become positive. The acceptor atoms have accepted an electron and become negative ions. So the internal field goes from plus to minus, and it is in the positive direction. So what would be forward bias? Well, forward bias, and we'll give the rules in just a minute, or just a few seconds. Forward bias would be that voltage across the device which is in opposition to the internal field. So if the field goes this way, we want a field from left to right, in a positive direction. We want a field going in the opposite direction, or the negative direction. So the right side would be positive and the left side would be negative. Forward bias always reduces the depletion width and lowers the potential barrier. Reverse bias, on the other hand, increases the depletion layer widths and increases the potential barrier. Forward bias is in opposition to the internal electric field. Reverse bias is in the same direction as the electric field. So if forward bias would be plus here, minus here, reverse bias would be plus on the left and minus on the right, and that would make the depletion regions wider. We can think of this one more way. For forward bias, if we put a positive voltage here, we are pushing holes into the depletion region which cover up some of the negative ions, so it makes this smaller. And if we have reverse bias, so this would be a negative over here, we're pulling holes away from the depletion region, which uncovers more negative ions. So any way you look at it, we should be able to, just with a few seconds thinking logically, determine which is the direction of forward bias and which is the direction of negative. Okay, so now we're ready to look at the device structure tree. We're at this part, the bipolar junction transistor. We're going to do the same transition on the right side when we go from the relatively simple structure of the metal oxide semiconductor to the metal oxide semiconductor field effect transistor, or MOSFET. But I have to put out a warning here. The transition from the PN junction to the bipolar junction transistor is quite a bit more involved than this transition here. And the reason is that we had one junction in the PN structure. We have now two junctions, and at each junction of these two, we have two currents. So we have a lot of knobs and buttons to push and different doping densities. So this is a fairly complicated structure. And we can at least get a hint of that by going back to the PN junction. This is the general expression for the current density. If it was current, I would just have an A here, the cross-sectional area in both of these terms. But when you have one junction, we have a hole current and we have an electron current. Here we have two junctions. At each junction, we have a hole current and an electron current. So this is going to be a relatively complicated journey, but we're not going to go into all the detail. Some of the detail is in the text, not all of it. By the way, I should mention that this is the general case. We know it's a general case because we have hyperbolic cosines and hyperbolic sines. If it was the short base, then this would be a linear function, and this would be a linear function. And of course, as we saw last, I shouldn't say of course, but we saw last time that the general case reduces to the nice short base case when the LP is much larger than the widths of the neutral. In this case, will be neutral base regions. And just one last figure before we jump into the BJT. Again, this is the PN junction, and we see that there are four possibilities. We have holes going from the P side into the N side where they become minority carriers. We have electrons going from the N side where they're majority carriers into the P side where they are minority carriers. In both cases, we have a combination of drift and diffusion, and that is exactly what happens in the BJT, although it happens in two places, not only one, because there are two junctions. Okay, so here we see a picture of the BJT. we have three different parts. We have something called the emitter, labeled E, the base, labeled B, the collector, labeled C. The base will be the control element. The emitter emits charge into the base, and the collector collects it. Now, that's not always the case, and I'd like to begin with a rather strange case, which is possible. The device designer comes to me, the fabrication engineer, that's what I used to do with my life, and he says, I want you to make me a symmetrically doped. All regions, in this particular case, all three regions are doped 10 to the 16th, and therefore they have identical depletion regions on both sides. It may seem like a very silly thing to do, but it's just a starting point. Again, there are two barriers, one at the emitter base junction and the second at the base collector junction. Each of those barriers has a magnitude of 0.72 because 10 to the 16th doping is 0.36, and since it's 0.36 on the P side, 0.36 on the N side, the total barrier here is 0.72, and the total barrier here is 0.72. Now, this is what I make for my friendly device designer, and he decides to forward bias each junction. And let's look at the hole currents. Just looking at the hole currents. We're not going to now deal with the electron currents. There's a hole current from the emitter to the base, and there's a hole current in the collector to the base. And they're both forward biased to the same extent. They both have the same magnitude of forward bias. Therefore, we expect these currents to be precisely the same. Here is the current from the emitter to base. Here's the current from the base, from the collector to the base. And what happens when they collide? When they get to the center here, that boom, one meets the other, they cancel each other out, and there is no net current. Now, that is not particularly desirable. It has some utility. Basically in switches, we can switch to a state in which this does exist. It's called the saturation mode, but it's not ideal for amplification. And amplification, I don't mean that an electron comes from the emitter into the base and all of a sudden it takes some, I don't know, super vitamins or something like that, and it gets a lot bigger, and it's collected in the collector, and it was puny over here, and now it comes out that it's much bigger and stronger. No, that's not the case. Amplification is all about control. We control the current from the emitter to the collector, which is large current, by having a little bit of current in the base. So a little bit of current controls in the input, controls a lot of current in the output. So let's take a look at the desirable characteristics. I should have perhaps put in parentheses, these are the desirable characteristics using the BJT as an amplifier. First, we want the ratio of inductive charge at the emitter to the base should be as large as possible. We want lots of current flowing from the emitter to the base. Okay, and that makes sense because we want lots of current at the output. Okay. In the BJT, the output will be the collector current, and the input will be the base current. So we want the ratio of collector current to base current to be as large as possible. Second, all charge injected from the emitter we would like to reach the collector. This is a structural issue. This depends on two things. How wide we make the base. We want to make it as narrow as possible, and we want to make it as pure as possible so that no charge which enters the base recombines before it reaches the collector, and that's a big deal. Today, essentially, all of the charge that enters the base reaches the collector. So generally we don't have to worry about this today if we make a good device. Okay, we want essentially no charge injected from the collector into the base. What does that mean? We don't want this. We don't want lots of charge injected from the collector into the base. And we control that by doping and by reverse biasing the base to collector junction. Forward biasing the emitter to base junction so we get lots of charge pumped into the base. Reverse biasing the base collector junction so very little current flows from the collector into the base. Okay, and that again is a structural issue. We make the emitter highly doped, get lots of charge. We make the collector lightly doped. There's not much to inject. And we forward bias this junction, we reverse bias this junction. So it is a structural issue and a biasing issue. Now all this comes about in the sort of summarized in the energy band diagram. The emitter this is for PNP. The emitter is very heavily based, so the Fermi level is close to the valence band. The base is n-doped, so it's closer to the conduction band, but it is much lighter doped than the emitter. And the collector, it's very lightly doped. So it's still n-type. Actually, it almost looks like it's p-type here. That should not be. This should be down a little bit further. So this is really, I'm sorry, no, it is p-type. So this is n-type. So the Fermi level is closer to the conduction band. This is p-type, so it's closer to the valence band, but it's much further from the valence band than the emitter. So this is a lightly doped p-type, this is a moderately doped n-type, and this is a heavily doped p-type. Now this is for the NPN, and let's see if I can get these both in one picture here, and you notice it's exactly the same except it's flipped. The n-type is very heavily doped, the base being p-type is p-type closer to the valence band, but much further than this distance here. And then the collector, it looks like it's n-type, very slightly n-type. So that's the NPN, and this is the PNP. Now we go back to the PNP. Generally, we'll be using the PNP for most of our discussions, but not all of them. But this is the PNP, which you should recognize immediately, and we're going to look at the electric fields. The electric fields at the emitter base junction are negative, and the reason is this is P, this is negative ions on the depletion region, positive ions on the base side, so the field goes from right to left. It is negative. The slope depends on the doping. Notice that this is very steep, which represents a very high doping. This is much less steep and much lighter doping at the depletion region on the base side. In the base collector junction, on the other hand, we have the N side of the depletion region is positive and the P side is negative, so the internal field goes from left to right in the positive direction, which is why this electric field is positive. And since this doping here is N and this doping is N, the slope here should be the same as the slope here, and hopefully it is. And then the slope here is much more shallow because the doping is much lighter. Okay, now if we look at the charge densities, the charge density in in the emitter side at the depletion region is negative and narrow. In the N side, in the base side, it is much wider and therefore much lower. The area here is equal to the area here, because every positive ion sends out an electric field which lands on a negative ion. And the same thing here, we have a relatively moderately doped, which gives a fairly wide depletion region. This width here is the same as this width here, and this width here is the same as this width here. This is the total depletion region electric field. This is the total depletion region for the charge density, and the area and the base side is equal to the area on the collector side. And we can do the same thing with an NPN, and I probably won't be able to get these on the same picture, but here we know minus, plus for the electric field, and here we have plus, minus. Notice the slopes are the same here, and very heavy slope on the very highly doped N side. So it's the same thing. Everything's just reversed. And if you look at the charge density, we flip it, and we flip it at the base collector region here. So everything is relatively straightforward and hopefully makes sense. Okay, so we're ready to look at at least qualitatively, how this crazy thing works. So here's the operational considerations, and we're going to start with a relatively straightforward qualitative description. Okay, so here again is hopefully what's becoming a little bit more familiar to us. Figure 14.7, it shows a chunk of holes, this is a PNP, which are thrown in from the emitter into the base, and they continue and are collected by the collector. And here we've added another component, because this is a PN junction right here, PN. So wherever we have holes going from the P into the N, we also have electrons going from the N into the P. And if it's forward bias, we open the gate, so to speak, we lower the barrier, and we have two flows, one from base to emitter, and the other from emitter to base. We're trying to minimize this because this is the input right here between this line and this line, and this is the output between the collector and the emitter. This is called the common emitter configuration. Okay, very simple. We haven't talked about, in this particular case, any charge which comes from the collector into the base. That will add later on. Okay? But arrow 1 is current injected from emitter to base, and emitter to base passes through the base and is collected, and that is denoted by arrow 2. This is a relatively large current, which we mentioned before, which is controlled by a much smaller current, represented by arrow 3. Why is 3 less than arrow 1? Because the doping here is about 100 times, sometimes more, than it is in the base. So if we have a high doping in the emitter, much lower doping in the base, there's a lot more stuff, in this case holes, which can flood through from the emitter to the base than there are electrons in the base, because there's just less of them. The gate is open the same for both. The difference is how much stuff can go through in each case. So for phishing operation of the BJT, we would like the doping, in this case the N is the doping, we'd like the doping in the emitter to be much greater than the doping in the base. And we would also like, and we'll get to this a little bit later on, we'd like the base to be much more narrow than either the emitter or the collector, specifically the emitter. And we would also like the base doping to be greater than the collector doping. It doesn't have to be much greater like it is here, but we'd like it to be greater, and we'll see why. And again, the biasing is the emitter base junction is forward biased so that we can get large amounts of stuff which floods from the emitter to the base, and the base to collector junction is reverse biased, so we have a large electric field which sucks up the charge that is floating, or diffusing, I should say, through the base. So that's the rationale. These NE, NB, and NC refer to the emitter base and collector doping densities, and the W's, of course, are the lengths or the widths of the emitter, the base, and the collector. Okay, so to put this a little bit on a quantitative scale, we define two figures of merit. One is called the base transport factor, alpha T. T refers to transport, and that's just equal to IC divided by IE. We want this number to be literally just about 1. The higher the better. Can't be over 1 because IE is the source of charge, and we can't have more coming out than is we started with. So, however, we would like IC and IE to be very, very close, and we can attain that. And the way that we attain that is there's no recombination in the base. So if there's no recombination in the base, whatever comes in, namely IE, goes out, namely IC. And this will be pretty much 1. And that's a good thing. That's always good. So for modern transistors, this essentially we just take it as being 1. And then we have the emitter efficiency, which is the more interesting of the two. And that is just IE divided by IE plus IB. That we would like to be close to 1, but it can never be 1. And in fact, we don't want it to be 1. Because if it was 1, that means that IB would be 0, which is a logical impossibility, because we always, no matter how light the doping is, we're going to have some electrons which are going to be pushed from the base into the emitter. So IB cannot be equal to 0, and if it were equal to 0, we'd have no input current. And no input current, you have no control. So we don't want this to be 1, but 0.99 is pretty darn good. So this guy, essentially, we assume is going to be equal to 1, and this one, 0.99 is pretty good. Okay, and we define this thing called alpha DC, which is their product, but it essentially is equal to the emitter efficiency gamma. So let's see where we can go with this. Let's take a little bit further. Here we have an NPN, just to be a little bit nasty. The N emitter, P base, N collector, and here we have electrons. This is the big guy right here, 1. That's electrons going from the emitter into the base, and here's the little guy, which is holes going from the base into the emitter. Okay. And if we go back to the PNP, I suggested that we'll be switching from NPN to PNP, but mostly we'll be analyzing the PNP. We're just making some comments about the NPN. They really work exactly the same. Okay, so if we assume the transport factor is 1, then we have the emitter efficiency. In this case, we just wrote it as, this is the definition, IE over IE plus IB, but since IE and IC are the same, we can substitute IC wherever we see IB. And we can simply rearrange that in equation 14.7. And finally, we find the ratio of IC over IB just by collecting all the ICs in one place, and that is equal to gamma divided by 1 minus gamma, and that is equal or defined as the beta. The beta is the ratio of the collector current over the base current. The higher that number is, the more efficiently the transistor operates. It's a figure of merit of the transistor, and it depends almost exclusively on the ratio of doping between the emitter and the base. If that number is high, the emitter is, for example, 100 times the base doping, then beta will be pretty close to 100. So if gamma, for example, is 0.99, that would be about a beta of about 100. And just some simple algebraic manipulation. We can solve for beta as a function of gamma just by basically taking this equation and first turning it on its head, and then just using basically high school algebra to find that gamma is equal to beta over beta plus 1. And we can see, for example, that if beta is 100, then gamma is about 0.99. So it's the same as we've seen previously. Okay. The beta depends on the ratio of doping densities. That's the predominant. That's the biggie. And it also depends on the ratio of the widths. As we'll see, ratio of the widths of the emitter to base region. We want to make the base narrow and the emitter wide. This will add factors of maybe 2 or 3. Here we're talking factors of 100. And the diffusion constant. Diffusion constant depends basically whether it's an NPN or PNP. The NPN always will have larger diffusion constants, so NPNs are a little bit more efficient. But here we're not even talking about factors of 2 or 3. We're generally talking about factors of 30 or 40%. So this goes from the biggest to the less and to the least. Okay, so let's continue our quantitative discussion. It's not really all that quantitative, but it's mini quantitative. We'll get into the fancier stuff probably in our next session. So we know that the excess carrier concentration, in this case the excess holes in the N-type material, is equal to the number of holes in the N-type material. This, for example, would be holes, emitters that come from the emitter in the N-type base, minus the equilibrium. That's where that 0 comes from. And the first term is this, the boost, and the second term is this one. So this is the amount that the equilibrium are boosted. For example, if BBE is 0.6 volts, this number here, this exponential, would be 10 to the 10th, a very big number indeed. And in the emitter, we have exactly the same thing. Electrons coming from the base into the emitter, we do exactly the same thing. They're also boosted, for example, if it's the forward bias is 0.6 volts. This would also be 10 to the 10th. What's the difference? This guy is 100 times this guy. That's the difference. All right, so, oh, by the way, I just made one correction here. I had this as EB for consistency. Let's make it all BE, base to emitter, the voltage between the base and the emitter. So that's just a notational issue. Okay, so let's go forward. Looking at the current density, this is the current density of holes which are emitted from the emitter into the base, and that's just equal to the emitter current divided by the area, which is essentially the collector current divided by the area, because all of those holes are picked up by the collector. And likewise, the diffusion current of the electrons, which are emitted from the base into the emitter, is just equal to IB divided by A. We take the ratios of these two quantities, and we find immediately that the ratio is equal to the ratio of the equilibrium concentrations, and if the Pn is 100 times the Np, then the current densities also are in the ratio of 100, and that is about as good as we can get. Okay. We also said that the beta is dependent on the widths of the base region and the emitter region. So if we have, we know diffusion current is proportional to the derivative of the excess carrier concentration with respect to x. If it's linear, then this x is just WB. And here, this would be in the emitter. This is the electrons, which are thrust, I shouldn't say emitted because they're thrust from the base into the emitter. So when they get into the emitter, they diffuse, and the diffusion parameter, which is of significance in the emitter, is the emitter width. So if the emitter width is much larger than the base width, we get an extra added factor of maybe 2 or 3, and finally the diffusion coefficients in the emitter and the base. If it's a PNP, the diffusion coefficient in the emitter will be of holes, which are thrust, which are emitted. The diffusion coefficient in the emitter will be electrons, which come from the base. The diffusion coefficient in the base will be holes, which come from the emitter. Okay, and generally, electrons have higher diffusion coefficients or diffusion constants than holes because the mobility of electrons is higher than the mobility of holes. And d over mu is kt over q. That's the Einstein relationship. So if mu is higher, d is higher because the ratio is kt over q, which depends only on the temperature. Lastly, but certainly not least, really interesting and fun part of this, we're going to try to express the emitter efficiency, that's that gamma, in terms of material constants. Of course, gamma is the whole ballgame. The alpha t is basically 1, so we generally don't have to worry about that. And here we just see another diagram. In the base, we have a short base, so we have a linear variation of excess carrier concentration. In the emitter, we have a long base, and that's why we have this exponential roll-off. Okay, so we know that the emitter efficiency is equal to this ratio, and we can write it like this, equation 1416. Again, just another representation that we have lots of current going from the emitter to the base, and a little bit going from the base to the emitter. But this is essential. It's always there, and it better be there because otherwise we have no control. We just want to make the ratio as large as possible. Okay, so we just repeat these two current densities. These are the big guys, the small one and the big one. And generally, to make it more indicative of the fact that PNP and NPNs are kind of kissing cousins, instead of saying N sub P, we say N sub E, which is the number of charge in the emitter. Here's the excess concentration in the base. So again, this is the big one, and this is about 100 times less than that. Okay, so we know that this whole business here is just equal to the equilibrium value multiplied by the boost, and we're going to assume that it is an exponential decay. It could be, exponentials are more general. It can collapse to the linear if we have a short base, but if it's not a short base, then we use the exponential form. Okay, now the law of mass action, this is for equilibrium. That's why we have the zeros here. We know that the number of equilibrium electrons and the number of equilibrium multiplied by the number of equilibrium holes is equal to Ni squared, which is Ni is the intrinsic 10 to the 10th. So this would be the number of equilibrium electrons. This would be the number of equilibrium holes, and those are related, of course, to the doping density. N sub E, N sub E would be N sub A, the emitter doping concentration. So we can write, basically take this guy and stick it into equation 1421, and we get 1423 and 1424. So anyway, we write two expressions, and these involve the boost. This is the exponential boost. This is the exponential decay. Could be exponential, could be linear, doesn't matter. And NE, if you're confused about NE and NB, have no fear. We're going to take the ratio, and from the ratio, we'll be able to see which one's smaller. Whatever it is, the ratio between the ends here, the big ends, is about 100. So let's just keep that in mind. So we just take the ratio of these two guys, and here it sits, and we cancel out everything that we can. The cubes cancel out, and the exponential terms here cancel out, and we're left with equation 425, and we bring the NB squared, the NB upstairs, and let's take a look at 1425 because there's a lot here going on. Now, these two terms are going to be different. Don't have to worry about that. I'll explain why we did not cancel these guys out. It's actually rather important. But, and here's the kicker, the numerator is much smaller than the denominator because the electron current is much smaller than the hole current, which means that NB is much less than NE. So even if I forgot what in heaven's name is NB, what is NE, oh, it's crazy, it's okay. You don't have to worry about it because I know this ratio is about 1 over 100, and it's all in here. This is the big guy right in here. So if this is about 1 over 100, this is about 1 over 100. So this top one is the doping density in the base, and the bottom one is the doping density in the emitter. The doping density in the base is about 10 to the 17th. The doping density in the emitter is about 10 to the 19th. We notice here, this is the diffusion coefficient in the emitter. Diffusion constant or coefficient, whatever it's called, is in the base. Here it's about 20% difference, depending on whether it's an NPN or a PNP. And here we want to take a look a little bit further by using the charge control model from Chapter 12. And we have two terms for the current. Remember, we have the area under the charge density versus position or versus length. In the one case, we have L sub P. This is the long base, and this is the short base. So we substitute in here, and we get W over L sub E. W is small, L sub E is big. This is a factor of about 1 to 2. So here we have a factor of 1 to 100. Here we have a factor of about 20%. And here we have a factor of about maybe 2 to 3. Now you ask the question, and it's a good question, why didn't I just cancel these two terms out? Because intrinsic is intrinsic. Well, we want to leave open the possibility that the intrinsic number in the emitter will be different than the intrinsic number in the base. For example, suppose the intrinsic number in the emitter is much less than the intrinsic number in the base. Then we can have all kinds of interesting things going on, and that's what we're going to talk about a little bit later on. So that is a materials issue. That is not a fabrication issue. It is not a biasing issue. And that will get us into something called the heterojunction bipolar junction transistor. Okay, so I'm going to skip over all this. This is actually rather straightforward. Just take a look very briefly at the output characteristics. Specifically, we see IB are very small. IB is on the order of microamps, but this is IC, and IC is in the order of milliamps. So this allows for the opportunity or the possibility of amplification, and you notice that the output current does not depend on the reverse bias. As long as the reverse bias is enough to suck all those holes in an NPN transistor, then it doesn't matter what the magnitude of that voltage is. So we'll continue this next time